For lesson 4, we are going to be talking about compound events. So for compound events, it is an event that consists of two or more simple events. So we're combining events and seeing how they affect each other. The sample space is what we're going to use for some of these probabilities. It is the set of all possible outcomes of a probability experiment. So we're writing out the entire sample space of every single scenario that could happen. So first, we're going to look at it making our sample space by using a list. So let's look at number 1. The 3 students chosen to represent Miss Krippinger's class in a school assembly are shown. All 3 of them need to sit in a row. So let's say we have Emily, Andrew, and Megan. So we want all 3 of them in a row. We're going to show all possible ways that this could be done. Rather than writing out the full name, I'm just going to do initials. So Emily can be first, followed by Andrew and then Megan. Or we can have Emily first, followed by Megan, and then Andrew. We can have Andrew first, followed by Emily, then Megan. We can have Andrew first, followed by Megan, and then Emily. And then last, Megan can be first, followed by Emily, and then Andrew. Megan first, followed by Andrew, and then Emily. So sample space, I'm not asking, how many outcomes here. I'm not asking certain probability. We're just saying these are all the possible ways that it could be done. Second one, you roll 2 standard dice. So we're going to list out the entire sample space. So we've got, you can roll a 1 and a 1, 1 and a 2, 1 and a 3, 1 and 4, 1 and 5, 1 and 6. Our first dice can be a 2, followed by a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6. First one can be a 3, 3 and 1, 3 and 2, 3 and 3, 3 and 4, 3 and 5, 3 and 6. First one can be a 4, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. First dice can be a 5, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. And the first one could be a 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So again, just showing all the possible scenarios. And it's important to do the sample space like this because a 1 followed by a 2 is different than a 2 followed by a 1, even though they might give you the same sum if you're playing like a game or something. The other way that we can find our sample spaces is by using tree diagrams. So a tree diagram is a diagram in which lines branch out from a central point to show the sample space. So it kind of looks like a tree with a bunch of branches. So for 3, suppose you toss a quarter, a dime, and a nickel. A lot of times the mistakes that I see people make is they'll branch it out and they'll do Q, D, N for quarter, dime, and nickel. But really when we're tossing a coin, what are we looking at? We are looking at heads versus tails. It does not really matter what the coin is. So let's say we've got our first one. First coin is either going to be heads or tails. So maybe I'm going to write this as coin number 1. Then you're flipping, let's say we started with heads. You flip the second coin. The second coin's either going to be heads or tails. If our first one had been tails, again, when we flip the next coin, it's either heads or tails. So this second branch here is talking about coin number 2. So coin number 1 is going to be heads or tails. You flip again, it's heads or tails. Flip again, it's heads or tails. Then in each of these scenarios, again, we're just doing the third coin flip. It's going to be heads or tails for each scenario. So this represents flip 1, flip 2, flip 3. When we are looking at the probability, so it's looking at what's the probability of two tails and a head. So it doesn't specify any of the order, it just says that we have two tails and a head. So we're looking for two tails and a head. So we're saying, okay, flip 1, heads, heads, heads. Nope, doesn't work. Heads, heads, tails, not enough tails. Heads, heads, then a tails, then a heads, not enough. Heads, tails, tails. Yeah, this branch right here is 1. Okay, starting over here. Tails, heads, heads, doesn't work. Tails, heads, tails. Yeah, that's two tails and a heads. Going over here. Tails, tails, heads. Yep, that works. That's two tails and a heads. Tails, tails, tails. No, that does not work. So we have 3 that work for two tails and a head out of the way that you can tell the total amount is on the bottom. How many do we have? This is 1, 2, 3, 4, 5, 6, 7, 8 total possibilities in the end, because it would be route 1, route 2, route 3, route 4, route 5, route 6, route 7, route 8. So the probability of two tails and a head, doesn't matter the order, is 3 out of 8. Okay, still looking at these tree diagrams. A car can be purchased in blue, silver, red, or purple. It also comes as a convertible or a hardtop. Let's draw our tree diagram and then answer the probability question. So we have 1, 2, 3, 4 possibilities to begin with. So 1, 2, 3, 4. So blue, silver, red, or purple, and then we have 2 scenarios after that, convertible or hardtop. So convertible or hardtop, convertible or hardtop, convertible or hardtop, convertible or hardtop. So our scenarios are blue, convertible, blue, hardtop, silver, convertible, silver, hardtop, red, convertible, red, hardtop, purple, convertible, purple, hardtop. So what is the probability of picking a blue convertible? The only scenario where that works out is this 1. And again, the total, we're looking at how many at the bottom. 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. A cell phone company is offering a special deal. If you choose from payment plans A, B, or C, and one of 4 different phones, you can choose a free gift of a case, a car charger, or a memory card. So, first thing we're looking at is we have 3 payment plans, A, B, or C. And I just like to spread out the first ones a lot because they start getting closer and closer to each other as we do more and more rows. So we have 3 payment plans, and then one of 4 different phones. So I'm just going to list it out as 1, 2, 3, 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then the last one, we can choose a free gift of a case, a charger, or a memory card. So we've got 2 C's. I'm going to say my case, I'm going to write it as C. My charger, I'm going to write it as H. So 3 gift choices. So case, charger, memory card, 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 and keep doing that. Go ahead and pause the video if I'm writing too fast for you. Okay, so we've got all our scenarios there. What is the probability that Adam will choose plan A, phone 2, and the car charger? So plan A, phone 2, and the car charger. That's this one scenario here. There's only one possibility. The total amount, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36 possible outcomes. And that's a lot to do. And the more that you add in, the harder it would be to kind of draw a tree diagram because it's going to take up your whole paper. So sometimes we don't actually need the sample space. Sometimes we just want to know what the total possible outcomes are. So for that, we can use what we call the fundamental counting principle, which uses multiplication of the number of ways each event in an experiment can occur to find the total possible number of outcomes. So let's look at this example. Alexandria rolls a standard die and chooses a letter from the words numbers. Find the total number of outcomes. So there's two things we're looking at here. We are looking at rolling a standard die, choosing a letter from the word numbers. So standard die has 6 outcomes. We can actually multiply 6 times. Well, choosing a letter from numbers, there's 1, 2, 3, 4, 5, 6, 7 possibilities. So 6 for the dice, 7 for the letters. You multiply those, there's 42 total outcomes. And if you want to check how that works, you could check up here. 3 times 4 is 12, times 3 is 36, which gave us the possible outcomes there. So now, for some of these, we don't really need the sample space because we know, okay, the probability of getting a 6 and an M, there's only going to be one scenario where that happens out of 42. Number 7, Kyle guessed the answers to 4 multiple choice questions on a test. If each question had 5 different choices, how many different answer combinations were there? First, I'm going to tell you the most commonly incorrect answer that I will see for this is 4 times 5 equals 20. That is wrong. Read carefully. Read that these are 4 multiple choice questions. Same thing when we have true or false ones people mess up on. So, guess the answer to 4 multiple choice questions on a test. And they each have 5 different answers. So question 1 has 5 possibilities. Times. Question 2 has 5 possibilities. Question 3 has 5 possibilities. Question 4 has 5 possibilities. So this was number 1, number 2, number 3, number 4. And we have to multiply the total possible ones. And when we multiply that out, there's 625 possible outcomes. So if you're just trying to guess on a multiple choice test and you have no background knowledge to guess, it's very unlikely that you're going to get a perfect score because that is very difficult to get. All right, go ahead and work on the homework.